Implicit Solutions, Level 1. In this video, we will learn about implicit solutions to differential equations. You might have heard the term implicit function from your study of pre-calculus and differential calculus. For example, in pre-calculus, you learn about conic sections, such as circles, ellipses, parabolas, and hyperbolas. These functions are typically represented by an implicit relation. In your differential calculus class, you learn how to take the derivative of implicit functions. For the most part, we usually deal with explicit functions, that is, a function in which the dependent variable is expressed solely in terms of the independent variable, along with some constants. For example, the following functions are explicit functions. In the same manner, an explicit solution to a differential equation is one in which the dependent variable is expressed solely in terms of the independent variable, along with some constants. In other words, the variable y appears once, either on the left or right side of the equation, and is also raised to the first power. In these videos, we can think of an explicit solution as an explicit formula of the form y equals phi of x, that we can manipulate, evaluate, and differentiate using standard rules. We recently seen various explicit solutions in the previous videos. Every single example from the previous videos involve explicit solutions. Unfortunately, once we start solving ordinary differential equations, our methods of solution do not always lead directly to an explicit solution. This is particularly true when attempting to solve nonlinear first-order differential equations. As a result, we have to be content with a relation or expression that defines a solution implicitly. In general, a relation of the form g of x and y equals 0 is said to be an implicit solution of an ordinary differential equation on an interval I, provided there exists at least one function that satisfies the relation as well as the differential equation on I. If you happen to solve a differential equation and found a solution of the form g of x and y equals 0, then there exists at least one function that satisfies both the relation, that is, g of x of phi of x equals 0, and the differential equation on an interval I. At times, if the implicit solution is fairly simple, we may be able to solve for y in terms of x, and obtain one or more explicit solutions. For the most part, there is usually no need, or, as a matter of fact, is just plain impossible to try and solve an implicit solution for y explicitly in terms of x. The best we can do is to numerically generate the graph of the solution and determine an appropriate interval of definition. For example, let's verify the following implicit solution. X squared plus y squared equals 9. And the differential equation to verify is y prime equals negative x over y. Just the way we verified explicit solutions of ODEs, we first need to find the derivative of the solution. Notice that we're going to have to find the derivative of this function by implicit differentiation, a technique first introduced way back in your differential calculus course. If you need a refresher, you can always look back at the Calculus 1 videos. Alright, taking the derivative of this function implicitly with respect to x, we obtain the following expression. Now, if we were to solve for y prime, we would obtain the following. Simplifying the expression, we see that y prime is equal to negative x over y. If we substitute y prime into the differential equation, we see that both the left and right-hand side match. Hence, this implicit function is a solution to the differential equation. Next, we need to find an interval I of definition. To find this interval, let's go ahead and plot this implicit solution. Recall that this equation describes a circle with center located at 0, 0 and with radius equal to 3. At first glance, you might be tempted to define the entire circle as your interval of definition. Unfortunately, this would be incorrect. Recall that a solution to a differential equation has to be differentiable at the given interval I of definition. Notice that this function would not be differentiable at x equals negative 3 and x equals positive 3. Because the tangent line at these points will be vertical and therefore undefined, meaning the implicit function is not differentiable at these points. As a result, we will need to label these points with open circles. Notice that this solution is now broken up into two semicircles. It turns out that we can actually find an explicit solution to this differential equation. Let's take a look at the implicit solution. Notice that we are able to solve for y in terms of x. All we need to do is to isolate the variable y. Doing that, we obtain the following expression: y equals positive negative the square root of 9 minus x squared. Notice that we were able to find two explicit solutions to the differential equation. The first is the positive square root of 9 minus x squared, and the second is the negative square root of 9 minus x squared. Notice that these two functions satisfy the relation, that is, x squared plus the first explicit solution squared equals 9, and x squared plus the second explicit solution squared equals 9, as well as the differential equation. Moreover, each explicit solution represents a segment of the implicit solution. The first explicit solution forms the top semicircle, and the negative explicit solution forms the bottom semicircle. In addition, notice that the domain of the explicit solution is defined from -3 inclusive to +3 inclusive. But, as we just saw, in order to satisfy the differential equation, these solutions can't be defined at x equals 3 and x equals -3. As a result, we have two options for our interval of definition. We can use the first explicit solution and define our interval of definition from -3 exclusive to +3 exclusive. Or we can use the second explicit solution and define our interval of definition from -3 exclusive to +3 exclusive. Either of these intervals can be used as our interval of definition. In a much later video, we will be required to choose one interval over the other. For now, either of the explicit solutions along with their intervals are acceptable answers. The final thing I want you to be aware of when dealing with implicit solutions is to make sure that any explicit solution that you happen to find has to be a real valued function. For example, say that we are asked to verify the following implicit solution: x squared plus y squared equals -9. Notice that the only difference between this implicit function and the one from the previous example is that this one is equal to -9. If we were to solve for an explicit solution, we would obtain the following expression: y equals positive negative the square root of -9 minus x squared. Notice that any value of x will force us to take the square root of a negative number, and therefore we are unable to draw a graph of this function, since it is not a real valued function. Although the explicit solutions are not real valued functions, they nevertheless satisfy the relation, and they also satisfy the differential equation. So we have to be careful when finding explicit solutions of implicit relations. The implicit solution might satisfy the differential equation, but an interval of definition cannot be determined because the explicit solution is not a real valued function. When this occurs, we say that the implicit relation is a formal solution to the differential equation. Keep in mind that the implicit relation is not a solution to the ODE, since no interval of definition can be defined in any interval. But the relation just happens to formally satisfy the differential equation. Alright, to sum up, a solution of the form y equals phi of x is called an explicit solution of an ordinary differential equation on the interval I. Many differential equations don't have explicit solutions. The best we can do for these equations is to eliminate the derivatives that appear in the equation and to simplify the equation into a derivative-free equation of the form g of x and y equals 0. This relation is called an implicit solution of the differential equation. Implicit solutions are perfectly acceptable and in some cases necessary, as long as the equation actually defines y as a function of x. Keep in mind that explicit solutions of implicit relations are sometimes difficult, if not impossible to solve for algebraically. In any case, explicit solutions are preferable, and you are encouraged to find them whenever possible. Alright, in our next video, we're going to cover a couple of examples illustrating how to verify implicit solutions to ordinary differential equations, as well as defining appropriate intervals of definition. Implicit solutions, Level 2. In this video, we're going to illustrate how to verify implicit solutions to ordinary differential equations, as well as finding explicit solutions and defining appropriate intervals of definition. Let's go ahead and jump straight into the first example. Verify that the indicated function is an implicit solution to the differential equation. If possible, find an explicit solution. Give an interval I of definition for each explicit solution. The differential equation is y prime equals x over y. The implicit solution to verify is y squared equals x squared minus 3. Alright, let's first verify this implicit solution. Let's start by taking the derivative of this function implicitly with respect to x. Carrying out the differentiation and applying the chain rule along with the power rule, we obtain the following expression. Next is just a matter of solving for the derivative, in this case y prime. Doing that, we obtain the following expression. Simplifying the expression, we see that the derivative is equal to x over y. The next step is to verify that the left-hand side of the differential equation equals the right-hand side. So we go ahead and substitute this expression into the differential equation as follows. Notice that both sides of the equation match. This means that the implicit solution is indeed a solution to the differential equation. Now let's determine an appropriate interval of definition. Let's start by plotting this function. Recall that an equation of this form describes a hyperbola that opens along the x-axis and is centered at the origin. Inspecting the graph, we see that the derivative will not be defined at the vertices because the slope of the tangent line at these points is vertical and therefore undefined, meaning that we need to exclude these points from the interval of definition. Next, let's check and see if we can find an explicit solution by solving for the variable y and obtaining an expression in terms of x. Looking at the implicit solution, we see that solving for the variable y is fairly straightforward. It's just a matter of taking the square root of both sides of the expression. Doing that, we obtain the following. Y equals positive negative the square root of x squared minus 3. Here we have two explicit solutions. One represents the upper and the other represents the lower half of the hyperbola. Notice that the domain of each explicit solution is defined by the inequality the absolute value of x is greater than or equal than the square root of 3. However, because this implicit function is not differentiable at the vertices, we need to exclude these values from the domain so that we can define an appropriate interval of definition. If we were to use the positive explicit solution, our interval of definition would be defined from negative infinity to negative square root of 3, exclusive, or from the interval positive square root of 3, exclusive, to positive infinity. If we were to use the negative explicit solution, we would have the same interval of definition, but this time, we would be using the bottom half of the hyperbola. In this example, we were able to find an explicit solution and use it to define an appropriate interval of definition. Keep in mind that this would not always be the case. It might just be impossible to find an explicit solution from the implicit relation. Alright, let's try the next example. The differential equation is y prime equals the quantity y minus 1 times the quantity 1 minus 2y. And the implicit solution to verify is the natural log of the quantity 2y minus 1 divided by the quantity y minus 1 equals x. Alright, let's first verify this implicit solution. We first need to find the derivative of this implicit relation. Before we proceed with the implicit differentiation step, let's first rewrite this expression in a more derivative-friendly form. Let's apply the laws or rules of logarithms that you learned in your Algebra 2 class. We're going to break apart the natural logarithm into a difference of logarithms, as follows. Now that we have the implicit function in this form, let's go ahead and take the derivative implicitly with respect to x. Carrying out the derivative and applying the chain rule, we obtain the following expression. Next, we need to solve for the first derivative, in this case, y prime. So we go ahead and factor out this term as follows. Next, let's go ahead and add the fractions by finding a common denominator and rewriting the numerators accordingly. Next, let's simplify the terms in the numerator. And finally, let's multiply both sides of the equation by the reciprocal of the expression inside the bracket. Doing this, we obtain the following expression for the derivative. After that, let's substitute this expression into the differential equation and verify that both the left and right-hand side of the equation match. Substituting the expression into the equation and simplifying the left-hand side of the equation, we see that both sides coincide. This means that this implicit function is indeed a solution to the differential equation. Now let's determine an appropriate interval of definition. The implicit relation is not a conic section, or an implicit function that you have encountered in your studies of mathematics. So let's first see if we can find an explicit solution. Going back to the implicit solution, let's try to solve for y in terms of x. We can achieve this by first exponentiating both sides of the equation and using the number e as our base. Doing that, we obtain the following. Next, let's multiply both sides of the equation by the quantity y minus 1. After that, we need to distribute the exponential term into the quantity y minus 1 as follows. From here, we need to move all the terms that contain the variable y into one side of the equation and the rest of the terms to the other side of the equation. Moving all the terms with the variable y to the left and the rest to the right side of the equation, we obtain the following expression. At this point, it's just a matter of factoring out the variable y from the left-hand side of the equation. Then we solve for the variable y by dividing both sides by the quantity 2 minus e raised to the power of x. Doing that, we obtain the following explicit solution. So we were lucky that we actually found an explicit solution to the differential equation. Now let's take a look at the graph of this explicit solution. Notice that this graph is not defined at x equals the natural log of 2. So we would expect to see a vertical asymptote at this given value of x. As a result, the graph would be split into two regions, which translates into two distinct intervals of definition to choose from. One interval of definition is from negative infinity to the natural log of 2 exclusive, and the second interval is from the natural log of 2 exclusive to positive infinity. Either of these two intervals are appropriate intervals of definition. Alright, in our next video, we will continue verifying implicit solutions to differential equations and go over slightly more challenging examples. Implicit solutions, Level 3. In this video, we're going to continue illustrating how to verify implicit solutions to ordinary differential equations. This time around, we're going to go over slightly more challenging examples. Let's go ahead and take a look at the first example. Verify that the indicated function is an implicit solution to the differential equation. If possible, find an explicit solution. Give an interval I of definition for each explicit solution. The differential equation is 2xy plus the quantity x squared minus y times y prime equals 0. And the implicit solution to verify is negative 2x squared y plus y squared equals 1. Alright, like in the previous video, let's go ahead and take the derivative of this implicit function. Taking the derivative and applying the product rule along with the power rule, we obtain the following expression. Next, we need to isolate the derivative term, in this case, y prime. In order to accomplish this, we need to move all the terms containing y prime and move them to one side of the equation, and the rest of the terms to the other side of the equation. Doing that, we obtain the following. The whole point of moving all the terms to one side is so that we can factor out the y prime term, as follows. From here, it's just a matter of solving for y prime. Doing that, we obtain the following expression. Having found the derivative, we proceed with the substitution step. Let's verify that the left and right-hand side of the differential equation are equal to each other. Carrying out the substitution, we obtain the following expression. Next, we go ahead and simplify the expression. Let's first distribute the quantity x squared minus y with 4xy, as follows. Then, let's go ahead and add both terms together. We're going to need to find a common denominator, and then proceed by adding the numerators. Doing that, we obtain the following expression. Simplifying the numerator, we see that all the terms cancel out, leaving us with 0 over the quantity negative 2x squared plus 2y, which simplifies to 0. both sides of the differential equation are equivalent. Hence, this implicit relation is a solution to the differential equation. Next, let's go ahead and assign an interval of definition. We first need to generate the graph of this implicit solution. This implicit function is probably not familiar to you, since it does not have the form of any conic section. So let's see if we can find an explicit solution. Notice that at first glance, it seems like it is plain impossible to solve for y, since we have two terms with this variable, and one of them is raised to the power of 1, and the other is raised to the power of 2. How can we possibly solve for y? It turns out that we can actually accomplish this. First of all, notice that the implicit solution contains a quadratic term, a linear term, and a constant term. Let's rewrite this expression by moving all the terms to one side of the equation, and setting the other side of the equation equal to 0. Lastly, let's rewrite the terms with the powers in descending order, as follows. This implicit function is essentially a quadratic equation of the form ax squared plus bx plus c equals 0. But in this case, instead of x representing the variable, we have y taking the place of the variable x. This means that we can use the almighty quadratic formula and find an explicit solution. The coefficient a, b, and c will be equal to 1, negative 2x squared, and negative 1 respectively. Substituting these expressions into the quadratic formula, we obtain the following expression. Simplifying throughout and dividing both terms by 2, we obtain the following explicit solutions. Y equals x squared, positive negative, the square root of x to the power of 4 plus 1. Next, let's go ahead and plot both of these solutions. The positive solution generates the following graph. The domain of this function is essentially all real numbers, from negative infinity to positive infinity. And this will also serve as our interval of definition. If we use the second explicit solution, we obtain the following graph. This function is also defined from negative infinity to positive infinity, and this interval also serves as an appropriate interval of definition. In this example, we had an implicit solution that was quadratic in form, and therefore, we were able to find an explicit solution by solving for y in terms of x via the quadratic formula. Alright, let's go over the final example. The differential equation is y prime equals the quantity negative 2x minus y over the quantity x plus 2y. And the implicit solution to verify is y squared plus xy plus x squared equals 0. Alright, like always, let's first find the derivative of this function. Taking the derivative implicitly and applying the power rule, along with the product rule, we obtain the following expression. From here, it's just a matter of solving for the derivative. To accomplish this, we're going to need to move all the terms containing y prime to one side of the equation, and the rest of the terms to the other side of the equation, as follows. Next, we go ahead and factor out the y prime term. From here, we go ahead and solve for y prime by dividing both sides of the equation by the quantity 2y plus x, as follows. Having found the derivative of the implicit relation, let's go ahead and substitute this expression into the differential equation. Substituting the expression, we see that this implicit relation is a solution to the differential equation. Next, let's check to see if we can find an explicit solution. Notice that this implicit relation is quadratic in form. It contains a quadratic term, a linear term, and a constant term. In order to solve for y in terms of x, we're going to need the quadratic formula so we can find an explicit solution in terms of x. The coefficient a, b, and c will be equal to 1, x, and x squared respectively. Substituting these expressions into the quadratic formula, we obtain the following. Simplifying the expression inside the square root results in the following expression. Y equals negative x, positive negative the square root of negative 3x squared over 2. Having found an explicit solution, we are ready to graph the expression and find an appropriate interval of definition. Unfortunately, we have a problem. Notice that the domain of the radicand is always going to yield a negative number, except at x equals 0. And as a result, we are forced to take the square root of a negative number. This explicit solution is not a real valued function. Since we do not have a real-valued function, we cannot assign an interval of definition. In the end, this implicit relation is a formal solution to the differential equation. We cannot say that this implicit relation is a solution to the differential equation since we cannot assign an interval of definition. Keep on the lookout for implicit solutions that formally satisfy a differential equation. To truly determine if an implicit relation is a solution, we need to be able to determine an appropriate interval of definition. So keep this little detail in mind. Alright, in our next video, we will go over the concept of a family of solutions.